All right. Good morning, everyone. So today we are starting module 3, Planarity. All right. Before we start, are there any questions or concerns regarding the last module or the writing exercise or anything? Let's make sure we don't have any backlog before we start the new module. All right. If not, let's begin. Okay. So let's consider a few graphs. So this is the first example. Right, that's K4. That is also K4. And that is also K4. Right? So all of these are drawings of K4. Right? But K4 itself does not need to be drawn in order to exist. So in that sense, a graph, as we have been discussing so far, is an abstract mathematical object that may have many different representations. So it may have different types of representations. So what are some types of representations of graphs? Can someone tell me? What are the different representations of graphs that you are familiar with?
Adjacency matrix.
Right, matrices. Okay, what else?
Adjacency list.
Adjacency list. Okay. So what are the different types of representations? Well, there are many. One is adjacency, or there is also the thing called incidence matrix. Those are the two matrix representations that are popular. You can also have adjacency lists. Okay. Well, and then there is drawings of a graph, which is the representation we are generally using in this course. We generally don't write down the matrices or lists. We just draw the graph. Drawings are also called embeddings. In some surface, the surface we typically draw on is the plane. Okay, but there are other surfaces that you can draw a graph on. Why not? So there are different types of representations and possibly many representations of each type. So what I mean here is if you're looking at the drawings of K4, then well, here are three drawings that look different. Right? Okay. And so until now we have been saying a graph, but what we have been really meaning is the underlying abstract mathematical object. And we generally draw it in order to visualize it. And we choose a drawing that is convenient for our purpose. Right? And there is a significant difference between some of these drawings. Can someone tell me what is the difference between this drawing and the other two drawings?
The middle drawing has two edges intersecting at a point which is not the terminal vertex.
Exactly. There is a point in the plane where two edges are crossing or meeting, and that point is not a vertex of any of those edges. Okay? It is not an end of any of those edges. Whereas that does not happen in these two drawings. Okay, good. So,
Sir,
yeah, go ahead.
sir, actually, I just entered now. So just can you just recap what you just said in the last 5 minutes?
Well, I'm not going to recap everything because you should be coming in at time, right? So you go through the first 5 minutes later. I will just say that this is the crux of what I've said, that a graph is an abstract mathematical object that may have different types of representations listed here and many representations of the same type. So the type I want to focus on today is drawings of a graph, and here are 3 drawings of K4. Okay,
Okay.
so that's the brief summary.
So basically, drawing is a representation of a graph, drawing or embedding.
Yes, it is a representation of a graph. Yes,
And here there are three different drawings of K4.
that's right. Okay. And in the second drawing, there is a point where 2 edges cross, but that is not an end of any of those edges. So that is a key point to note. Okay. So, in particular, we are going to restrict ourselves to drawings of a graph, or as we will call them, embeddings of a graph on the plane, because we are not going to focus on other surfaces. We are only going to look at the plane. Or if you like, a sphere, because everything you can draw on the plane, you can draw on a sphere and vice versa by stereographic projections. We will talk about that a bit later again. Okay, but hopefully most of you are familiar with this, or you can intuitively see this. Okay, so an embedding or drawing of a graph G. So in order to distinguish the graph from its embeddings, we will put a tilde. So this is G1 tilde, this is G2 tilde, and this is G3 tilde. And all of these are embeddings of K4. Okay? So an embedding or drawing G tilde of a graph G on the plane, or maybe I think it should be an embedding in the plane, is planar if in this embedding any 2 edges meet only at their ends. If they have a common vertex, common end. Otherwise, the embedding is not planar, not a planar embedding. Okay? So in particular, in our example, these two G1 tilde and G3 tilde are planar embeddings of K4. However, the middle one is not a planar embedding. Okay? All right, let's consider another 1 or 2 examples. For example, here is a graph with 2 planar embeddings that look different. We will talk about when 2 embeddings are the same or different later, but you can kind of intuitively see that these are somewhat different from each other. Can anybody point a specific difference to me? I know that we have not introduced terminology, but if you look at these 2 drawings, is there a specific difference you note between them?
The rightmost
Sir, I
vertex
think
It is
Yeah.
interior in one graph and exterior in another.
Okay. The rightmost what? The triangle you mean?
No, the rightmost vertex.
The rightmost vertex, like this one.
Yes, right.
Okay, okay. It has been flipped out. Okay, that is one difference.
If you
Sir, I
join,
think
uh,
there is another.
Okay, Krishnan, go ahead.
yeah, if you join an edge from the vertices in the middle to the left graph,
Hmm.
the graph is, I
Hmm.
mean, they
Hmm.
don't intersect with any other edges. But if you
Hmm.
join an edge between these
Right.
two vertices,
I see.
they,
I see. Good. Okay. Yeah. So what Krishnan is saying is, if I add another edge joining these two degree two vertices, in this case I get a planar drawing very easily. However, in the other case, I won't get a planar drawing of the new graph. So that is a key difference. Yes. Ananya, you had a difference as well.
Yeah, means actually there is a concept of a dual corresponding to an embedding. So
Okay.
I think
Can you explain that without going to the dual?
okay,
So you
without
are
not going
right.
to
Without going to the dual, can you explain that concept using some
so
more
without going
elementary concept? Yeah.
without going to dual, I think means
Hmm.
basically so if we go to dual, then we can say that their duals are not isomorphic, something like that.
Yes.
But
Yes.
what
Yes. You're
Christian
right.
yeah, but what Christian had said that in this graph there are only two vertices of degree two, and if
Hmm.
we join the degree two vertices in the first embedding, then the
Hmm.
will not cross any other edge. By cross, I mean it doesn't
Yeah. Yeah. I get
intersect
it.
other
Yeah. Yeah.
any other point. But
Yeah.
if we join the edges vertex of degree two in the second embedding, the edge will
Yeah.
cross.
That's fine. That's fine. But can you explain the dual thing without using the dual concept?
So yes, sir, yes, sir. So
Yeah.
okay, so I have to explain the dual thing without the dual concept, right?
Yes.
So
Anyone else sees a difference? So there is a concept called regions or faces actually. Can you use faces if you are aware of this concept and then explain the difference?
yes, sir, I got it, sir.
Good.
So you said that you have to use faces. So in the
Mm,
first embedding,
mm,
there is no face which is
mm.
adjacent to more than three faces. But in the second embedding, there is indeed a face which is adjacent to four faces.
To four faces. There are total four faces only in both drawings.
Yeah, there are total four faces, but in the first
Mm,
drawing, there is no face which is adjacent to four faces. By
I see.
adjacent, I mean they share an edge in common.
But what about this face? What about this face? It shares an edge with every face, right? So the way to look at it, yeah, sorry, go ahead.
Yeah, it shares an edge with every face. Yeah.
Yeah. So the way to look at it, so there is a concept called faces. I'm not going to define it rigorously right now, but intuitively you can see what the meaning could be. These are the four faces in this graph, in this with respect to this planar embedding of the given graph. And in this case, there is a concept of length of a face, which is the boundary of that face. This face has length 6, these two faces have length 3 because they are bounded by triangles, and the last face has length 4. Whereas in this, the second drawing, there is a face of length 5, 3, 3, and 5. If you look at the lengths of the faces, instead of getting 3, 3, 4, 6, you get 3, 3, 5, 5. And that is related to the concept of a dual of a graph, which we'll talk about later. Okay. But anyways, right now I'm not making things rigorous.
So, sir, by length of a face, we mean the
Boundary
regions
of,
around
yeah,
okay,
the length of
the
its
number of
boundary.
edges in the boundary of that face, right?
I'll give the formal definition later, but in this drawing, yeah, it is a number of edges.
Number of
When we
edges.
have cut edges and loops, you have to be a bit careful. So in this example, it is the number of edges.
Number of edges.
Okay. Okay. So there are some key differences between two drawings. All right. What about this graph? We have seen K4. K4 has planar drawings.
Can you scroll up a bit, sir, for that figure? So in this drawing, okay, so you're saying that the lengths of the faces in the first embedding and the length of the face in the second embedding, they are different.
Yes. Yes.
Okay.
Yeah. Which is basically related to what you are saying, dual of a graph. Okay. Okay, so now let's talk about K5. Can you draw a planar embedding of this graph?
Yes.
Yes? Okay, so how shall we go about it? Can you, yeah.
So can you just mark the vertices?
Yeah, V1,
Yeah, I
V2,
think it is possible to draw a planar
okay,
embedding.
let's first try to draw it and then see if we fail. Okay, so I marked the vertices V1 to V5. Go
So
ahead, Rajat.
first take the cycle V1, V2, V3, V4, V5 as it is.
Okay,
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 then draw V4, V1 and V4, V2 as they are in the previous drawing.
like this.
Is right. Then we can we can pull out V5 and V3.
Okay,
V5, V3
like this.
is right.
Okay,
Okay, and then V1, V3 we can pull it out also.
okay.
Okay, then this is the planar embedding.
Are you sure? Or are you missing one edge?
Sir, I
Yeah,
think the picture which you
No,
have drawn on
let him
the
complete. Let him complete. So, yeah, Rajat, go ahead.
yeah, this is the whole graph.
Are you sure? Or is there one edge missing? I see two vertices that are not adjacent. And in K5, any two vertices are adjacent.
Oh, this is not K5, right? This is K5 minus E.
This is K5 minus one edge. V2, V5.
Yeah, means in the previous drawing you drew K5
Oh,
minus V.
oh, you're right. Okay, my bad. I meant it to be K5 and I forgot one edge, so you were actually right. Thanks. I meant K5 itself and I had forgotten to draw one edge. So thank you. That is indeed a planar graph. And what about K5? Do you think K5 is planar?
No, I don't
No.
think.
Okay, okay. So K5 minus one edge is actually planar. And the graph I actually intended to draw is not planar. We will prove that in some time. Today or tomorrow. Okay, so I haven't told you what a planar graph is, right? But I wrote these examples. So a graph is planar if it admits an embedding that is planar. A graph G is planar if it admits a planar embedding. Right? So in particular, the first graph we looked at, K4, is planar because it has planar embeddings, at least one, right? So just because G2 tilde is a non-planar embedding of K4 does not mean K4 is non-planar. K4 is planar because it has planar embeddings. Okay?
However, the planar embedding need not be unique, right?
Right. We will talk about uniqueness. It may not be unique. So right now I'm just going to say it admits a planar embedding. Okay? And in fact, to discuss uniqueness, we also need to understand, or we need to make rigorous what we mean by unique. Right? Otherwise, G is non-planar. Okay? And in that sense, K5 is a non-planar graph. But K5 minus one edge is a planar graph.
Sir?
Yeah.
Yeah, I have a doubt. So if we know something about the planarity of G, can we say something about the planarity of its complement?
Um,
Is there something that?
right. Generally speaking, if the graph is planar, its complement will not be planar. And there is a reason behind that, which we will see later. In fact, you are giving me some ideas for uh, problems. Thanks. So generally, it's not going to be planar. There might be small exceptions,
Yeah.
but generally
Okay.
the complement will not be planar.
Okay.
Yeah, so I think Shrikant mentioned in the chat that planar graphs are generally sparse in the sense that they have a linear number of edges, and therefore the complement will not be sparse because it's a quadratic minus linear, so you get quadratic number of edges. Okay, so that is the correct reason.
Okay.
Okay, so we will come to all those very interesting questions, but before that,
Sir,
yeah, go ahead.
I think that K4 has a unique planar embedding.
We'll talk about that later because at this point we haven't really defined what it means for a planar embedding to be unique, right? So what do we even mean by unique? I mean, I could draw one, I already have two different drawings of K4 here. And why are they not different according to you? That requires a definition of uniqueness to be very specific. Okay, so we'll come to that later. Okay, good. So we know that K5 is non-planar. We will prove it. Right now we just assume it. What can you say about Kn? So up to n at most 4, you can check that they are all planar very easily. What about n at least 5?
Not planar.
Why?
Because K5 will be an induced subgraph of Kn.
Does it matter that it is induced or does it only matter that it is a subgraph?
Yeah. It's only a subgraph. Yeah, that's
Exactly.
true.
Exactly.
Yeah. Sorry.
So notice that every Kn, where n is at least 5, contains K5 as a subgraph. And if the graph sub K5 is non-planar, that will make the whole graph non-planar. I want you all to think about this for a few minutes. Right? So I'll write down an observation and I'll put it as a do it yourself. Every subgraph of a planar graph is also planar. Okay. Does anybody feel that this is not true or you don't immediately see why this should be true? And the idea is you take a planar embedding of your graph, and if you want any subgraph, you just look at that part of the graph. No two edges will cross because they did not cross in the original drawing. When I say no two edges cross, I mean they will not meet at a vertex at a point that is not an end of one of those edges, right? So I won't keep saying this long sentence. I will just say that two edges will not cross in the smaller drawing if your original drawing is planar. Okay?
Sir, I think it will be easy to show because every subgraph from a graph G, you can obtain that subgraph from G by simply deleting vertices and edges.
Exactly.
And
So
we
you
know
will
that
not
G.
introduce crossings,
Yeah.
right?
So
So you're
basically
already
the drawing
taking a
will.
planar embedding. Sorry, you're saying?
No, means since G is planar, we can start with any planar embedding of G, and we can
Exactly.
remove the desired any number of vertices or edges as we like, and
Exactly.
the resultant embedding will still be planar of
Yeah.
of some another graph
Yes, of a subgraph. Yes. Okay.
of a
So,
subgraph. That,
so this brings us to the decision problem. that if I give you a graph G, how do you decide whether G is planar or not, right? And as I sent a message yesterday to all of you, I wanted you to go over NP, co-NP, NP complexity classes, right? So if you're given a graph G, you want to decide whether it is planar or not. So there are two types of instances. There are the yes instances and the no instances. So yes instances are planar graphs and no instances are your non-planar graphs, right? And I want to discuss whether this decision problem, whether it belongs to NP and co-NP. Right? So what does it mean to belong to NP? It means that for a planar graph, if I give you a planar graph, you should be able to convince your friend easily that the graph is indeed planar. Right? So how would you do that? Supposing you have a certain graph and you want to convince your friend that this is a planar graph. How will you do
Provide
that?
a planar embedding of that graph.
Exactly. You will just show your friend a planar embedding of the graph, right? How you find that, it's your problem. That is an algorithmic question. It has nothing to do with NP and co-NP, right? So it's kind of intuitively easy that if you want to convince someone, you just show them a planar drawing and they can verify quickly that this is indeed a planar drawing. Okay? It's not a formal and rigorous proof, but intuitively, I hope you all see this. Right? So this is easy to convince someone. And in particular, the problem belongs to NP. What about co-NP? What about no instances? How will you convince your friend that a graph is non-planar?
Sir, I think you mentioned in lecture 2 that due to Kuratowski's theorem, we can say that this problem
Right,
belongs to
right,
NP.
right, that's right. Gutowski's theorem, yes, but let's say we don't know Gutowski's theorem. Let's say we are still in 1929.
But
In
how we can
2000, yeah.
do it with Kuratowski's theorem? It will not be polynomial time, right?
No, no, but co-NP and NP have nothing to do with polynomial time. So, I mean, they do, but they don't have to do with algorithms, right? So, okay, so basically what does Gutowski's theorem say? It says that if a graph is non-planar, then you can find a special structure, a subgraph in it, and that will be a certificate of non-planarity. Okay?
Okay, so all we need is a certificate.
Exactly. All we need is a certificate. We don't
I see.
need to find the certificate. That has to do with the complexity class P, polynomial time.
Okay.
Right? Okay? But what if we did not know Kuratowski's theorem at all? I don't want to use a theorem that we have not discussed so far, like in detail.
Then we need to check all the embedding of that graph.
Right. Does anybody see an easy way to check that a graph is, to convince someone that a graph is non-planar without using any fancy theorems?
But then, sir, how can we enumerate all embeddings of a graph, as Rajat said?
Exactly, exactly. Right. So that is exactly the point I'm trying to make here. That convincing someone that a graph is non-planar is significantly harder than convincing someone that a graph is planar. So that's my key point. Convincing someone that G is non-planar is much harder. And that is why it's not immediately clear whether this problem belongs to co-NP. So does the decision problem belong to co-NP? It's not clear. It is true, but that requires a theorem called Gutowski's theorem, which we will talk about in some time, or maybe in the next lecture. Okay? And that is one of the main things we are trying to prove in this module. Our main goal in this module is to prove Kuratowski's theorem. And on the way, see other interesting results about planarity. Okay? All right. Are there any questions or concerns at this point? Does everybody see the key point that convincing non-planarity is much harder than convincing planarity? Right? Because then you have to check every single embedding possible, and that just seems very difficult. Right? Okay. Good.
Sir, how
Yeah.
how old is Gutowski's result means?
1930.
19?
30.
1930. 1930.
Yeah. Okay. So the study of planar graphs is intrinsically related to the topology of the plane. Right? Some of you may have taken a course in topology, but the vast majority of you, and myself included, have probably never taken a course on topology. Anyone who's taken a course on topology?
I have.
You have. Who is that? Krishnan. Anyone else who has taken a course on topology?
Sir, I also have taken a course in topology.
Sir, in CMI, topology is a core course.
Oh, it's a core course. Okay.
Yeah.
Okay. Great. All right.
What is core course?
Right. So that makes sense. But typically, at least in CS programs in other places, you don't ever take a course on topology. And that is exactly what happened to me. I've never taken a course on topology. But that being said, half of my thesis was actually about planar graphs. So it doesn't matter. It's fine. We don't need topology of more complex surfaces. We just need the plane, and the plane is much more intuitive than other surfaces out there. Okay, so we will not go into other surfaces. All right, and in particular, there is one result from topology that we are going to require. It's called the Jordan Curve Theorem. How many of you have seen the Jordan Curve Theorem?
Sir, I saw it, but I don't exactly remember the result. I forgot it.
Okay, okay, good.
Basically, a curve which is not intersecting and is closed divides the
Right, so you've
plane
seen
into
it. Right,
parts.
yeah. So, right. So we will need the Jordan Curve Theorem, which we will not be proving because this is not a course in topology. We will just be using it whenever we find it useful. So here is the picture I want to give you. Let us draw a curve in the plane, a simple closed curve. I will define all of that, but you see this picture here. This is the curve C. When you draw a curve in the plane, a simple closed curve, what it does is it breaks the plane, the rest of the plane, into two parts: the interior of the curve and the exterior of the curve. Okay? And both of these pieces, the interior and the exterior, they are connected. It's called arcwise-connected in topology. We will write down the definition. The key point is, if you take 2 points in the interior, you can connect them by an arc that does not cross the curve. Okay? So that is what Jordan Curve Theorem says. Let me write it down, and I will abbreviate it to JCT, any simple closed curve. So that is something we need to define. C in the plane, let me call the plane P, partitions the rest of the plane. So what do I mean by rest of the plane? P minus C into two disjoint arcwise connected that we need to define open sets. For those of you who may not recall because you have lost touch, closed set, what is an example of a closed set? You take 0, 1 interval with 0 and 1 included, and the open set is the same interval where you remove the two ends, 0 and 1. Okay? So it should be fairly clear that if you remove the curve, then the inside and the outside, the interior and the exterior, they are going to be open sets because it contains everything, but it does not contain the boundary C. Okay? So you can get arbitrarily close to the boundary, and that's basically what it means to be an open set. Okay?
But if any of the regions contains the boundary C, then it would not be open.
Right. If you take the closure, then it will not be an open set. It will become a closed set.
So basically, we are excluding the boundary from both interior and exterior.
Yeah, that's right. Right now we are talking about P minus C. Therefore, the boundary has been removed.
So by C, we mean boundary of C.
Yeah, the curve itself is C.
Okay.
Yeah? Okay.
Okay.
Good. So we need to define all these terms, simple closed curve and arcwise connected. So let's go through the formalities so that we have the formal definitions, but we are not going to need too many technicalities so long as we understand the intuition. Okay, so what's a curve? A curve is just a continuous image of a closed unit line segment. Right? So you take the unit line segment and you take any continuous image of it. Okay? It starts at one point and it ends at another point. So long as it's continuous, it's a curve. Okay? And what is a closed curve? Well, think of it like path versus cycle. We want to now end at the same point where we started. And so in that sense, it's the continuous image of a circle. Okay? So the difference between the unit line segment and the circle is that it starts and ends at the same point. And so in that sense, the image would be something that starts and ends at the same point. Okay? Notice that there is a difference between these curves that I've drawn and this curve that I drew for the example. And that difference is that this curve, when you talk about the continuous image, it's a one-to-one mapping. It does not intersect itself. And that is called a simple curve, right? So a curve is simple if it does not intersect itself. In other words, the mapping is one-to-one. right? So a simple closed curve is one where you cannot cross the curve again at any point, right? So this would be a simple closed curve. Okay, and now what the Jordan curve theorem is saying, once again, to remind you, is that this is your curve, then you will get two parts, the interior and the exterior. And in this drawing, it is easy to see because it's a very sort of harmless curve. It's not a super complicated curve, right? So you can kind of see that there are exactly two regions. And the other part we need is we need to define what arcwise connected is. So let me write that here. A subset of the plane is arcwise connected if any two of its points can be connected by a curve lying entirely within the subset. So let's take an example. If you look at this curve I've drawn here, let's say I take one point in the interior and another point in the interior. Then what this is saying is that you can always go from that point to the other point while staying inside the interior of the curve. Okay? And in that sense, the interior and the exterior are going to be arcwise connected open sets. Okay? So these two sets are called the interior and the exterior. Okay? Are there any questions or concerns regarding these definitions? Don't worry if you are not too familiar with topology. The specific technical terms, you are not going to require them on your assignments or anything, right? We are basically going to be doing graph theory, but we need to know what we are talking about. So we need to make things a bit rigorous. Also, we will compromise on rigor when it comes to the topological side of things, right? But we won't compromise on rigor in the graph theoretical side of things, because that is the main point of this course. Okay? All right, so okay, so that's about it. In the next lecture, I want to prove why K5 is non-planar using the Jordan Curve Theorem. But before that, let me tell you an anecdote, because we are almost at the end of the lecture. So I'm trying to wrap it up. How many of you have seen a proof of the Jordan Curve Theorem?
Sir, I think we saw one in complex analysis, but I'm not too sure.
Okay. Anyone else who has seen a proof of the Jordan Curve Theorem?
Proof of Jordan Curve Theorem.
Yeah.
I think, yeah, I also saw, but not Jordan Curve Theorem is something similar result I saw in complex analysis.
Okay.
Complex analysis.
So, right. So when I was taking a graph theory course during my master's with Robin Thomas, he told us about the Jordan Curve Theorem when he started teaching planarity. I should mention that planarity is a topic that I enjoyed the most in my first course in graph theory. And I think that is partly why I decided to go for graph theory further. That's how much I enjoyed planarity. But when he was telling us about the Jordan Curve Theorem, I just could not understand why this requires a proof. Right? So I came from a CS background. Both my bachelor's and master's are in computer science. And I just could not understand why such an obvious result would require a proof. Um, so I asked Robin during the lecture that why does this need a proof? Like this seems obvious to me. And the class burst out into a, there were math students and there were CS students. Um, Mostly the math students burst out into a laughter because most of them had seen a proof, and to them it was obvious that a proof was required. The CS students were mostly in the same situation as me, so they kind of empathized with me and were almost thankful that I asked the question. And then Robin went on to explain why it does require a proof. I think Robin even proved it for us, but we are not going to prove it in this course because I would rather focus on the graph theoretical aspects of the course. So I just thought it was interesting the difference it made depending on the background you came from. Yeah. So, anyways, so that's yeah. Go ahead.
Is there any reference which also gives considerable weightage to even the topological aspects of planarity?
To topological graph theory, is that what you mean?
Yes.
Yes. So there is a book. If you're interested in topological graph theory, there is a book by Mohar and Thomason. It's the same Thomason who proved Thomason's theorem in the last module.
Okay.
So they have a book on topological graph theory. I don't remember the title, but if you just search, you'll be able to find it.
Okay, sir.
Yeah. They might even give you a proof of Jordan Curve Theorem. So Thomason gave a graph theoretical proof of the Jordan Curve Theorem. That I don't think I remember how it goes, but he basically proved the result using graph theory. Yeah. Any other questions or concerns? So tomorrow we will prove that K5 is non-planar using the Jordan Curve Theorem. Okay. And again, we will rely a little bit on intuition. And in the topological aspects, we might compromise slightly on the rigor. Otherwise, we will turn this into a topology course, which I don't want to do. Okay. So we will not compromise on the rigor in the graph theoretical aspects of the course. Okay. So if there are no more questions or concerns, feel free to leave the meeting. That's the end of today's lecture. We'll continue tomorrow.
So, sir, in the next lecture, we'll prove that K5 is non-planar using Jordan Curve
Yes.
Theorem.
Yes, in particular, we'll prove that K5 is non-planar. Yeah.
But, sir, can it means without using Jordan Curve Theorem, Jordan Curve Theorem, can it be shown that K5 is non-planar?
Typically, in most sources, you will see a proof using Euler's formula.
Yeah, means I know a proof that K5 is non-planar, but I do not
Yeah.
know
I
whether
believe the proof you know is using Euler's formula. We will also see that later. But I would really like to see go through the more topological proof, because it tells you more about the structure of K5 that is really crucial into making it non-planar. Because what Euler's formula does is that it tells you that there is too many edges in the graph, but it doesn't tell you much about the structure of K5. Okay, so we will also see a proof using Euler's formula, which is probably what you have seen earlier.
no, but sir, I am not sure whether my proof using Euler's formula. So can I just tell my idea how to
Yeah,
prove that
sure.
K5 is non-planar?
The lecture is officially over. Let me stop recording and then
Also,
you
a
can
small
tell me.
question. When
Yeah.
you'll start evaluating the assignment, second assignment?
I already started and I might make the marks for problem one available soon.
Okay.
I'm not done yet, but I will be finishing problem one soon.